Hey everyone! Today, we're putting on our detective hats and diving into the chemistry lab to solve a classic puzzle. We're going to be talking about a technique called acid-base titration. Now, that might sound a little technical, but trust me, it's a super powerful method, and you'd be surprised how much it affects on daily lives. So, let's set the scene. Imagine you're in a lab. You've got this beaker in front of you. It's filled with an acid. You know what acid it is, say hydrochloric acid, but you have absolutely no idea how strong it is. Is it super concentrated? Is it really diluted? How in the world do you find out? Well, that's the exact mystery we're here to solve today. With any good mystery, you can't just jump to the solution. First, you've got to get to know the key players, understand the scene of the crime, so to speak. So before we can figure out our acid, we first need to get a handle on the basics. What makes an acid, and what makes a base a base? All right, let's get into it. Our investigation really kicks off with the fundamentals. What's the difference between an acid and a base, anyway? Think of them as two sides of the same chemical coin, each with its own unique personality. Okay, some of this might be a throwback to your high school chemistry class. We all know acids, like what's in a lemon, taste sour, right? And bases, maybe like a baking soda and water mix, feel kind of slippery and taste bitter. But for what we're doing today, the single most important clue is that last one. Acids and bases neutralize each other. They cancel each other out. That's huge.
But to really get to the heart of what's going on chemically, we need to zoom in a bit. There's this idea called the Bronsted-Lowry theory, and it gives us a super clear definition. It all comes down to one tiny particle, the proton, which is really just a hydrogen atom that's lost its electron. According to this theory, an acid is just something that gives away a proton. And a base, it's something that takes that proton. That's it, a donor and an acceptor.
And take a look at this. You can see that exact exchange happening right here. You've got your acid, HCN, and a water molecule just hanging out. That little acid molecule donates its proton over to the water, which in this case is acting like a base because it accepts it. It's like a perfect little chemical handshake happening at the molecular level. And this is the absolute key to our whole mystery. When that proton transfer happens, when an acid and a base react, we call it a neutralization reaction. They literally cancel each other out. And what do you get? Two super stable things, good old water and a type of compound we call a salt. Remember this reaction because it's exactly how we're going to crack this case.
Okay, so we've got our background clues all lined up. We know our players. Now it's time to bring in the main tool for our investigation. It's called the titration method.
So, what is titration? Well, at its core, it's just a very, very carefully controlled neutralization reaction. The whole idea is to take our mystery solution, the one with the unknown concentration, and react it with a solution that we know the exact concentration of. By measuring precisely how much of our known solution it takes to completely neutralize the mystery one, we can just do a little math and work backwards to find the answer. Pretty clever, right? And the procedure itself is super methodical. Step 1, you take a very precise amount of your unknown solution. We call that the analyte, and put it in a flask. Step 2, you add just a couple drops of something called an indicator. We'll get to that in a sec. Step 3, you use this long glass tube with markings on it called a burette to slowly, drop by drop, add your known solution, the titrant. And finally, step 4, you stop the instant that indicator tells you the reaction is done. So, all of this careful measuring, the slow dripping, the constant swirling, it's all building up to one single critical moment. The success of the entire investigation hangs on finding that one perfect tipping point. But how do you know when you've hit that point? You can't see the molecules, right? You need a signal, and that's where that indicator comes in. Choosing the right pH indicator is everything. Think of it like a little spy in the solution, waiting to give you the signal that the mission, the neutralization, is 100% complete. And it's not a one-size-fits-all kind of thing. There are tons of different indicators out there. A chemist will pick a specific one based on the acid and base they're using. You can see here each one changes color and a very specific pH range. So if you're mixing a weak acid and a strong base, you might pick something like phenolphthalein, because you know the tipping point will be in that slightly basic range. Okay, let's put ourselves back in the lab. You're at the burette. You let one drop fall into the flask. You give it a swirl. Nothing. The solution is still totally clear. You add another drop, swirl again, still clear. But you can just feel it. With every single drop, you're getting closer and closer to that critical point. And then it happens. One
Single drop hits the solution, and bam! Instantly, the whole thing flashes from colorless to this vibrant, stunning pink. And this time, when you swirl it, the color stays. It doesn't fade. It's this beautiful, persistent pink. That is the moment.
That right there is the end point. That's the signal you've been waiting for, and the second you see it, you shut off the burette. Done. So what exactly is the endpoint? It's literally just the point where that indicator changes color for good. It's the visual proof, the smoking gun that tells us we've added exactly enough of our known base to neutralize every last molecule of the unknown acid. It's the most important clue we're going to get. All right, case closed. Well, almost. We found our endpoint, we stopped the titration, the lab part of the mystery is solved. But now, let's zoom out a bit. Why does this actually matter? Why is this technique so incredibly important beyond just a chemistry classroom? This is where we put that final clue to work. We look at the side of the burette and read exactly how much of our known solution we used. Since we know its concentration, and we know that the acid and base neutralize each other in a set ratio, we can plug those numbers into a pretty simple formula. And just like that, we can calculate the exact concentration of our original mystery acid. Mystery solved, for real this time. And don't think this is just for one or two specific chemicals. Not at all. Titration is a super versatile tool. You can use it to figure out the acidic or basic properties of literally hundreds of different substances, from simple inorganic compounds to complex organic molecules. So, why should you care? Well, it's because this stuff is everywhere. In medicine, titration makes sure the dose of an active ingredient in your pills is exactly right. In environmental science, it's used to check the acidity of rivers and lakes to make sure ecosystems are healthy. And in the food you eat, it's used for quality control on everything from your morning orange juice to the cheese you put on a sandwich. It is a huge deal.
So, if there's one thing to take away, it's this. Titration isn't just some random lab experiment you do in school. It's a fundamental, incredibly precise chemical balancing act that is essential for ensuring the quality and safety of things we rely on every single day.
When you think about it, our whole investigation hinged on a single drop of liquid that made the solution change color. It just makes you wonder, right? If one tiny detail like that can make sure a medicine is safe or a river is healthy, what other seemingly small things are out there, all around us, having a huge unseen impact on our world?